Alright, so we're going to begin by discussing applying pressure to solids. So whenever we apply a force to a solid, it changes shape. And so we talked about this a little bit earlier when we talked about inelastic collisions, because as two objects, even if they seem very hard, collide with each other, there's a little bit of compression which applies a force over distance and leads to a loss of kinetic energy. So once again, we're applying a force to a solid and seeing that it changes shape. And we say that the solid behaves elastically, meaning that once the force is removed, the solid returns to its original shape. And we saw this when we talked about springs. So springs behave elastically. That's why instead of being called spring potential energy, is often called elastic potential energy. So you apply a force, the spring changes shape, you remove that force, it relaxes back to its equilibrium position or original length. So we're going to introduce two new vocabulary words. The first is stress. And stress is the force per unit area applied to the solid. And this force per unit area actually causes the deformation. And our next vocabulary word is the strain. And the strain is the amount of deformation, or the amount that the object actually changes shape. And stress and strain are going to be proportional to each other, so linearly proportional to each other up to a certain point. And we're going to stick in the range where they are proportional to each other. And so we're going to end up introducing some proportionality constants in here. There is a point where you apply so much stress that the object never returns back to its original shape, and then you can also apply so much stress that the object actually breaks. So we're going to stick in that realm where they are proportional to each other. Alright, so we're going to first talk about one dimension, where we're going to pull on an object and it's going to change shape only in one dimension. So what we're going to do here is we have, say, a metal post sticking out of a wall here. And we're going to apply a force through the tension to the end of the post. And that's going to cause it to stretch out some delta L compared to its original length. So when we construct our equation here, we're going to look at force per area, and the area that we're talking about is the force that the area is actually applied to. So the area that we're talking about down here is going to be what we call the cross-sectional area. So in our case, since we're talking about a metal post, and I've obviously drawn it to look like a circle, we're just talking about the area of a circle here. So like if we took a slice of the post and looked at that slice as area. We're not talking about the whole surface area of the post, just the area that the force is applied to, which is the circle or the end cap of the post. And we're going to set this equal to delta L, which is the amount that the post is stretched, divided by its original length. And our proportionality constant in this case is going to be what we call Young's modulus. And Young's modulus is going to have units of pascals. Now, Young's modulus depends upon the material that's being stretched. So something like steel is going to have a very large Young's modulus, and something like rubber is going to have a smaller Young's modulus. They're still pretty big numbers, but steel is definitely going to be bigger than rubber. So the amount something stretches turns out to be inversely proportional to the Young's modulus. And now keep in mind, we're mostly going to be dealing with very, very tiny numbers here. If you walked up and pulled on a steel post, you're obviously not going to see any noticeable stretch. So we're going to have answers that are going to be in like the millimeter range, or fractions of a millimeter. Alright, so the next modulus we're going to talk about is the shear modulus, or what we're going to call elasticity of shape. So what I'm going to have here is a box, and you have to remember this is a box that goes into the page. This is not a rectangle. And I'm going to apply a force not down on top of the box, but across the top of the box. So we're applying a force across, so we're doing what we call a shearing motion. So if you think about shearing a sheep, you run the clippers across the surface of the sheep. You don't like plunge them into the sheep. That would be bad. That's not your purpose there. You just want to remove the wool. You don't want to hurt the sheep. Remember, the area is the top of the box. And that's then going to cause the top of the box to jut out some delta x compared to its original height. And of course, you're going to get a corresponding jut up in the back. So when we write this formula, we're going to have force per area equals delta x over h. And our proportionality constant, as already hinted by the title, is the shear modulus. Also, it's going to have units of pascals. And the shear modulus is different than the Young's modulus, and once again, it's also different for each material that you might be applying a force across. Another way of looking at this is, we actually used to do this in a lab, but somewhere along the line it got deleted, is you would have your lab bench, so you'd have your table, and you would take a meter stick and extend it over the edge. And then you would apply a weight. So we'd apply a force due to gravity in the y direction. And that would then cause that same meter stick to sort of bend down. So in that case, the amount it bends down would be delta x. In the area that you're applying it to, because the force of gravity is in the negative y direction, would actually end up being the end cap of the meter stick. So it's like taking this here and rotating it over here. So the area here would be the end cap of the meter stick, and then h would be the length of the meter stick, or 1 meter. It has to be the amount it actually hangs over, so it'd be less than a meter. So you can see I've taken this same diagram here, and I've rotated it sideways, so the force of gravity is the same as this force applied here. So the area would be over the end cap of the meter stick. I mean, we would actually use the deflection, how much it bends down, to find something else, and I can't remember what that was. Alright, so the last one in this section we're going to discuss is elasticity of volume, and that's going to involve the bulk modulus. So here I've taken our solid object and I put it in a container fluid. And this allows a uniform squeeze. So we have pressure being applied from all dimensions. You have to remember it's also going to extend out into the z direction that we don't ever talk about. And that's actually going to compress the object. So it's actually going to cause a decrease in volume. Now, when we talk about this, we talk about a change in pressure. We don't change into a force per area. And that's going to equal the change of volume over the original volume. Now we do have to put a minus sign in here because pressure and volume are inversely proportional to each other. So as we increase the pressure, so we have a positive delta P, you're going to get a decrease in volume, or a negative delta V. And we're going to finish this out by putting in the bulk modulus. And if we write this out a little bit fuller, we have to remember it's pressure final minus pressure initial, and then we have volume final minus volume initial divided by the original volume, or volume initial. So we can't forget that those are deltas and not just volume and pressure. As I said, B stands for the bulk modulus. Also going to have units of pascals. And once again, these are going to be different than Shear modulus and Young's modulus, and also different for different materials. And when you go to use the constant table that's linked in the constant table links in Blackboard, make sure you look at the top. A lot of these constant tables that are linked are going to be in terms of a certain number of power of 10. So they make it so that it's all in terms of the same power of 10, so you can look down the table and easily compare them. If something's 20 compared to 200, you know which one's bigger than the other. But you would then have to look up at top and realize when you plug something into an equation, there's like a times 10 to the 9 you need to multiply it by. So make sure you're looking at the top of the table, like the header row, to make sure you're getting the units correct on everything.